Hey everyone, and welcome back to this class, Modern Deep Learning in Python, Deep Learning in Python Part 2. In this lecture, we are going to talk about one of the newest and most common optimization techniques these days, the Atom Optimizer. Atom deserves its own lecture, as these days, it's often considered the go-to default for those doing deep learning. Sometimes, instructors like to introduce Atom by saying it's like RMSprop but with momentum. I think this might be a little confusing, because as you'll see later, TensorFlow implements each of these algorithms, so all you need to do is call a function. So there's an Atom Optimizer function and an RMSprop function. But the RMSprop function also lets you add a momentum term. So you can have RMSprop with momentum, but that doesn't give you Atom. It's just RMSprop with momentum. So it's not exactly the same as Atom. Simply adding a momentum term to RMSprop doesn't quite give you Atom. Atom does, in a sense, add something like momentum to RMSprop, but in a very specific way. You'll see this in the upcoming slides. There is one key piece of theory that I think is essential to understanding Atom, but I originally covered it in the batch normalization section of this course. The specific topic I'm referring to is exponentially smoothed averages. So you may want to check that out first and then come back here to get a better idea. I'm going to review these concepts in the next few slides, but if you want to skip ahead and watch the lecture on exponentially smoothed averages now, please feel free to do so. Okay, so the main idea behind the exponentially smoothed average is this. Suppose at first all I want to do is calculate an average. So I've collected some data I'll call x. I have x1, x2, x3, all the way to xt. Now we know that in order to calculate an average, all I need to do is sum up all these x's and divide by t, the total number of x's. We call this the sample mean. Now suppose I have so much data that I can't store all the x's. Is there any way that maybe I can calculate this average more intelligently? And indeed, you can see that if I rearrange the equation for the sample mean, which I'm now going to call m, I can write m of t in terms of m of t minus 1. And so now, instead of having to store all the x's, all I need to store is the previous m and the current x, from which I can calculate the current m. Now we see that there is this 1 over t term. Well, it's reasonable to ask, what if we set this 1 over t term to be constant? Now we get back what looks precisely like the cache update from RMSprop. So it's reasonable to ask, what is the cache of RMSprop really estimating? And in fact, it's estimating the mean of the square of the gradient. And because we eventually take the square root of this in the parameter update, you can see now why this method is called RMSprop. RMS stands for root mean square. You might also remember that the mean of a random variable can also be phrased as an expected value. And in particular, when we take the expected value of the square of a random variable, we call this the second moment. In general, the expected value of x to the n is the nth moment of x. So e of g squared is the second moment of the gradient, and we calculate it using this exponentially smoothed average. We're going to refer to it as v for the rest of this lecture, since the second central moment of a random variable is the definition of variance. If you remember your probability class, then all this stuff will help connect the dots. But if you have no idea what I'm talking about, then Wikipedia is a good source of review for standard probability concepts, like moments and mean and variance. Now, since there is a second moment, it's reasonable to ask, is there a first moment as well? And of course, this would just be the expected value of g. We call this m because the first moment of a random variable is the definition of the mean. Because the Atom update makes use of the first and second moments of g, using exponentially smoothed estimates, This also explains the name of the algorithm, ADAM, which stands for Adaptive Moment Estimation. Notice how this looks a lot like momentum, which we discussed earlier. Usually momentum is just implemented by adding a momentum parameter to the velocity, rather than doing this weighted average, but the weighted average method is sometimes used as well. This is why people sometimes say ADAM is like RMS prop with momentum. So to get to our destination, which is describing the ADAM update, we're going to combine these two pieces, the first and second moments of G, or as we've been calling them, M and V. But before we do that, there's still one more important concept to discuss. If you want, I would strongly recommend trying to implement the exponentially smooth average on a time series signal like a sine wave with some noise added to it. What you should discover is this acts sort of like a smoothing function. It ignores a lot of the very rapid random spikes, but it follows the main trend of the signal, which is the original sine wave. In the field of signal processing, we call this a low-pass filter, because the high-frequency changes are being filtered out. The problem with exponential smoothing is, just like RMS prop, what should we initialize the output to? The output is supposed to depend on the current value of the input plus the last value of the output. But since there is no last value of the output for t equals 0, we typically just set that to 0. But in doing so, we then set the initial value of the output to something like 0.01 times the first input. This is assuming your decay rate is 0.99. So initially, your output is going to be biased towards 0. Is there anything we can do about that? So there is a technique called bias correction that makes up for this. We divide by 1 minus the decay to the power t. As you can see, when t is small, we're dividing by a very small number, which makes the initial value bigger. This is good because the initial value was too small. Let's do an example to make things super clear. Given a decay of 0.99, our original output would be y1 equals 0.01 times x1. But corrected, it would be 0.01 divided by 0.01 times x1, which is just x1. y2 would be 0.99 times 0.01 times x1 plus 0.01 times x2. Corrected, it would be 0.497 times x1 plus 0.503 times x2. This also makes sense because it's about half of x1 plus about half of x2, with a bit more weight on the most current value. We can also see that when t approaches infinity, the bias correction term approaches 1, so we quickly converge to the standard exponentially smooth average. The important part is that our output now has the correct range of values when compared with the input for all values of the input, including the initial ones. Now that we've discussed bias correction for exponentially smooth averages, you might guess that we are going to apply it to the exponentially smooth averages we've been talking about, in particular M and V. So if we call M hat the bias corrected version of M, and V hat the bias corrected version of V, then we can formulate our ADAM update. Note that there are two different decay rates for M and V, which we'll call beta 1 and beta 2. Typical values for beta 1 and beta 2 are 0.9 or 0.999, somewhere in that range. And epsilon is again a small number like 10 to the minus 8 to avoid division by 0. So that was a ton of stuff, so let's recap. ADAM is a new, modern adaptive learning rate technique that is the default go-to for many deep learning practitioners. It combines two proven techniques, RMS prop, which gave us the leaky cache, and momentum, which speeds up training just by continuing to go in the same direction it was going before. We saw that these two methods can be generalized by observing that they estimate the first and second moments of the gradient. ADAM also adds bias correction, which makes up for the fact that the exponentially smooth average starts at 0, and hence the initial estimates are biased towards 0. There is one caveat when it comes to ADAM and other adaptive learning rate techniques. A paper was released in May 2017 titled The Marginal Value of Adaptive Gradient Methods in Machine Learning. I've added this paper to extrareading.txt so you can check it out if you want. The paper showed that, experimentally, regular gradient descent achieves better test performance than these adaptive learning rate techniques. This was surprising to many because, as I mentioned earlier, people often just default to ADAM. So this is why I like to say stick to the fundamental principles. Hyperparameters were meant to be optimized and everything is data dependent. This means for all of you who are asking, what are the best rules of thumb? I get that it's uncomfortable to have to make a lot of choices all at once. This is the case even for me. But just keep in mind, someone can publish a paper tomorrow proving that your rule of thumb is actually wrong.